This project was chosen because it combines the mechanical build with the motor unit alongside the electrical components and the computational side with the 3D imaging software. We took inspiration from an abundance of DIY laser scanner projects available to build, which involve a stationary laser and camera directed at an object on a rotating platform, so the object itself is rotating 360 degrees while the laser remains stationary. This method means the contour of the laser is analysed to form a point cloud. Our project takes this idea and adds a new dimension by rotating the laser and camera itself instead of the object. This vastly improves the scanner and increases its versatility, since the object is no longer limited to a small enough size to fit on the rotating platform. Our platform rotates up to 360 degrees, which allows us to scan even an entire room, so it's not limited to a single object. We split the roles of this project into 3 different components: the mechanical side, the electronic configuration, and the computational processing, and this is how we did it.
During the build process, it became apparent that our laser was not strong enough to scan in a fully lit room. As well as this, the lab around us had very varying light levels during testing, which meant that it was hard to optimize the computer program to see the red light on an image. We decided it would be easiest to create a consistent light level and remove all ambient light from the laser scanner by building this tent around it. It has the additional benefit of also blocking any of the laser's light, which means that it had no issues with going in people's eyes as they walked past the project or when things went wrong, and it spanned more than we were expecting it to. Another issue was when we attached these wooden blocks which act as stabilizers. This was due to the fact that the shape of the turntable is very asymmetrical, so it was hard to get it to balance perfectly, and it meant that the motor could not spin as we intended it to. So adding these blocks just created a little bit of extra balance, which improved the final image.
So we needed to scan an environment, and in order to do that we used a servo motor to precisely control the angular position of the stand. So we attached the servo motor to digital pin 9 on the Arduino, which can send out a PWM signal. PWM signal, or a pulse width modulation, is a timed pulse. So a 1 millisecond pulse sets the angular position of the motor to 0, a 1.5 millisecond pulse sets the angular position to 90 degrees. Then we use a compiled for loop within the Arduino code to sweep through all of those angles and send a different pulse width modulation signal for each individual step. The PWM signal also kind of restricts our motor to a 1 degree step, and this limits the resolution we get on our final image. And using some trigonometry, we find that to be calculated to be about 7 millimeters separation. And to improve this, we thought we could use a gear DC motor or a stepper motor, which is a finer increment on the angle, or use the servo motor to output a torque, which, using a system of gears, we can control a certain angle increment into.
The camera and laser have a separation of 45 centimeters, and due to the angled wing that both objects sit upon, this creates two lines that intersect in the direction that both of them face. This creates two perspectives upon the object, one from the laser beam on the left, which has an imaginary plane in the direction that the laser beam faces, and another one from the camera which intersects the laser beam. This is similar in concept to how having two eyes allows us to perceive depth. There are two steps in scanning the object. The first one involves panning the laser across the object, so the motor rotates the angled arm around, and this allows the laser beam to pan across the object. The webcam then identifies the red pixels in the image, so in this case the red pixels are from the laser beam, and creates a 2D coordinate of each red pixel in the image. This coordinate is also stored with the angle that the motor is currently sitting at, so that the image can then be processed and we can create a 3D plot. To avoid the software crashing from having too many data points, we only took every 5 red pixels. This is an arbitrary vertical resolution and can be changed depending on the capabilities of the hardware that the code is running on. But for our specific implementation, the vertical resolution of 5 was fine. The next step is then to process these data points to make a 3D coordinate of each white pixel and to plot it. To do this, the laser can be treated as a vector plane, as mentioned in the direction of the beam. The camera has a set of 2D coordinates and motor angles, which can then be converted to 3D coordinates by finding the intersection of each of the points on the laser plane, which is done by treating the webcam as an imaginary line that extends the laser plane, and by considering the angle of the motor, which allows for the depth to be perceived. These 3D points can then be plotted to produce a scan. We did this all in processing due to its native capabilities with handling Arduino communication, webcam images, and graphics processing.
In the future, we would want to use a more powerful laser so that our project can work in conditions with higher light levels. This would remove the need to control the environment as much as was required for this project. Furthermore, this would allow us to scan objects further away from the scanner, since the laser won't stop dimming at such close proximity, and the camera will still be able to detect the red pixels from the laser at larger distances. Additionally, the distance between the laser and the camera could be increased. This would widen the scanning area and allow us to scan larger objects. However, this would need to be implemented alongside the more powerful laser so that the red pixels can still be detected by the camera at larger distances. And finally, a motor with finer increments would allow a higher pixel density. This is because more data points would be plotted per sweep, and therefore would result in a sharper final image. This could be achieved with the gear system, for example, instead of the servo motor that we used.
Our project models the vast capabilities of laser scanning, but on a very small scale. If we were to scale it up, we'd be able to model buildings like this one. However, the lasers and the cameras used in this process are very expensive and we're way beyond our budget. A few alternative applications can be scanning rooms into video games or animations, as well as using it on extraterrestrial planets by mounting it onto the top of a rover, and it can be used to map the terrain of other planets.